a homomorphism, right? So this is a homomorphism. Of our modules. So a isomorphism of our modules would be a homomorphism of our modules that is what? That's also a bijection, right? And not just that, it is a, so is f from m to n and our module homomorphism, right, with f inverse from n back to m also in our module homomorphism. Now, for vector spaces, there's some very beautiful theorems, like if you have a linear transformation, right, which is invertible, okay, from one vector space to another, then there's a theorem that says that the inverse is necessarily linear. I'm not sure if that theorem is available for our module isomorphisms. But if it is available, it's in here. Most likely. It's definitely for vector spaces, right? You can also talk about the kernel. What would the kernel of an R module homomorphism be? It would be M and M, such that what? Such that f of m is equal to 0, right? And you can talk about the image which would be what? That would be f of m, such that m is an element of m. And I believe you can prove that the kernel is a submodule of m, and you can prove that the image is a submodule of n. I think you can do that. Yeah, well, it doesn't say that yet. Let me hold off on that. Maybe there's something funky with zero divisors that messes things up. Let me just hold off a second here. And there's also notation. So this homomorphism of our modules, the set of all such things, is denoted as follows: hom r m n. Oh, or homer mn. No one says that. I don't even say that. Let's see here. Any R module homomorphism is also a homomorphism of additive groups, but not every group homomorphism need be a module homomorphism, because the module action condition doesn't have to be satisfied. The unqualified term isomorphism, when applied to R modules, will always mean R module isomorphism. And so, like in this context, he has notation. He says M isomorphic to N. In that case, if there exists an isomorphism. All right. So proposition 2. Proposition 2 has all kinds of fun facts about homomorphisms. Let me write them down for us. Proposition 2, rather. So, first of all, phi from m to n is R mod homomorphism if and only if phi of x plus ry is phi of x plus r phi of y. In other words, you can combine the conditions 1 and 2 here, into just one condition. Just check linearity, as I would call it, right? So that's nice. Still can do that. And that has to be for what? For all x and y in M and R in the ring. I feel bad for Jenny. She went all the way over there. They just did that. Man, that's annoying. 2. If we have homomorphisms, right? So if we have, if phi and psi are in the R modulo homomorphisms from M to N, right? Then guess what? You can define new R modulo homomorphisms by what? You can add them, and what else could you do? You can scalar multiply them, right? So like phi plus psi and R phi are also in the R modulo homomorphisms from M to N. How would you define these? What's the definition of phi plus psi? What's the definition of R times phi? How would you define these? Very good. Yeah. So point-wise, right? And same for down here, right? It's just R times phi of M. So we can add maps. We can scalar multiply. We can R multiply maps. Yeah.
See, that's why I was confused by the like. You see how like when we're talking about Galois here, like we were fixing stuff.
Mm-hmm.
If R's in the ring, that's why I was asking if he like fixes R, but I don't think it means in the same way because that R is just popping out on the linearity of first part proposition 1.
Yeah.
Because we're not saying phi of R, phi of Y. We're just
Right.
We're really just kind of saying that you can pull it out. It's like a quote unquote constant.
Yeah. Let's see here. So we've got M, we've got N, we've got L. Right, so we've got phi going from M to N. We've got psi going from N to L. So we can look at the composite going psi composed with phi, I believe, from. So I think I copied that down wrong. Well, I copied something down wrong. Psi goes from M to N. Oh, I've mixed my letters up. So I'm not following. So I'm going to go with what's on the board rather than what's in the book, if it's okay. So then psi composed with phi is going from M to L. But anyway, more to the point here, the composite of composable R modulo homomorphisms is once more an R modulo homomorphism. The proof of any of these things makes a wonderful test question, but really boring lecture. Okay, so like, but just for kicks, how would you prove that this is true? You just do what?
I would construct the first one and the second one.
Yeah, we do psi composed with phi, and we'll use number 1 here, right? Look at x plus ry. So that gives us psi of phi of x plus ry, which gives us psi of phi of x plus r phi of y, applying 1, right? And then applying 1 once more, psi of phi of x plus r psi of phi of y, which of course is psi composed with phi, plus r. Yes, excuse me, you're right. Sorry, psi composed with phi of x plus r psi composed with phi. Y, yeah, sorry about my handwriting getting a little bit wild there, but yeah. So it's really just definition of composition and item numero uno. And then finally, with addition and multiplication above for composition defined, you can look at hom hom r m to m forms an R algebra under composition of maps, right? So like if you take two homomorphisms, R module homomorphisms from M to M, and you compose them, you get another R module homomorphism from M to M, right? And so forth. And in fact, the last example has a name. This is called definition. The endomorphisms, R endomorphisms of M is that. So endomorphisms. Endomorphisms of M. It's called the endomorphism ring of M and will often be noted end R or just end M when the ring is clear from context. All right. Such maps are called endomorphisms. In fact, I have a set of linear algebra notes somewhere where instead of using linear transformation, it just uses homomorphisms for linear transformations. If you really wanted to go all out, you could then use endomorphisms for your linear transformations from V to V, you know, if you want to make sure that the students are thoroughly confused. Go for it.
An R algebra under composition.
Right. So after we do all of this in linear algebra, the next thing we do is we look at the quotient spaces, yeah? So since M is a additive group under addition, you know, a module is an additive group under addition. This is proposition 3. If you have R ring and M an R module and N a submodule of M, then we can talk about M mod N, which is what? That is the set of X plus N such that X is an element of M, right? That's the factor group. And this can be made into an R module. The above is an R module via the following. So what do you think we're going to do? R, let it act on X plus N. How should we do that, do you think? What do you think the definition of the R module action is going to be here? How about we just do r times x, because that's defined, right? Because remember, m is an r module, so r times x is defined, right? We just do that, plus n. So this is the proposition, is that if you have a r module and you've got a submodule n, then you can look at the quotient module, m mod n, and make it into an r module by this natural action. And there's a natural projection map, pi, from m mod n to what? M, I guess. Is that it? Yeah, to m. By, what's the definition? Pi of x plus n is just what?
Pi of x, I'm sorry. No, it would be,
Something in m.
yeah, so x is an m.
Yep, that's it. Is a R module homomorphism. Like pi would be an element of what? Pi would be an element of hom R from where? From m mod n to m, right? And what else? What's the kernel of pi?
Just the identity.
What is everything pi sends to 0?
0.
What is 0 in the quotient? What's the idea of the quotient? M mod n it's a way of formalizing the concept that everything n we're treating as 0. Everything in n as in nanu nanu, not to be distinguished, not be confused with m as in mummy. So like the kernel is just, it's just n. It's the thing we're squashing. Now, the proof of this is very straightforward, and it's on page 348 to 349. When do you have to start practice today?
I don't know, because we don't really have practice in that.
Oh, okay, cool. Then maybe we'll get to a good, because I'd like to finish this up, and then I'd like to talk about the next section, which is on free modules. That's probably where we'll stop there.
Yeah, let me call my coach and make sure. Just take a break.
Yeah, take a second here. Hey, what do you know?